Great. Okay, so today we are going to be going over section 3.5. Let me kind of make endpoints on this. About right there, and then about right there. Okay, so we're going to go over section 3.5, which is on rational functions. And look, slow me down if you need me to slow down, but this section is a little bit longer. It's a little more in depth, and you'll notice this test doesn't have as many sections as previous tests, but I'll tell you the content in these next few sections is a lot. So that's the reason why. The very first thing your book talks about. So today we're going to go over the rational function, and we're going to talk about the domain of the rational function, the graphs of the rational function, and everything that really pertain to that. And before we really get started, we've got to define what a rational function is. And your book defines a rational function as any function that has a top and a bottom function. Okay, so we're talking about fractional functions now. Okay, that's what this is about. So fractional functions are rational functions. Good way to think of it. If we look at, we've seen some of these already because I've asked you about their domain. And the book does stick to polynomial, where P and Q here, P of X and Q of X, are polynomial functions, okay? So rational functions, when it comes to the book in this section, will be polynomials over polynomials. So for example, if we had, and this should look a little familiar, if we had like 2x plus 1 over 3x minus 4, right? This was straight out of section 2.6. And in that section, I asked you, what is the domain? Right? What's the domain of this function? That's all we did in that section in 2.6. And we said, or actually later on we went to other things, but one of the main concepts in 2.6 was the domain. So what is the domain? Well, we set this denominator equal to 0. And we really say it can't equal 0. And then we solve for x. We add the 4 and divide the 3, right? Add the 4, divide the 3. And we found out that x cannot be 4/3. It cannot be 4/3. And really for the domain, we stated it in interval notation. And we said x can be anything as long as it wasn't 4/3, right? Negative infinity to 4/3, and then there was a union, and then 4/3 to infinity. This was back in section 2.6, the very first part of 2.6. Today, though, one of the first things we're going to do is investigate what happens at this domain restriction. Okay, we're going to investigate what happens at this domain restriction. What happens at 4/3? Why did we just say, actually, we know it's undefined there, right? If we plug that in, this denominator would be 0. So it's undefined. Well, can we find out what actually happened? So we're going to get to that point. Or, no pun intended. We'll get to that part here in a minute. But before we get there, the book and myself, we're going to focus on the graphs of these rational functions, because typically rational functions have a very distinct look, okay? And there's two distinct things about them. So let's look at a basic example of one. You know what? Let me get this looking kind of pretty. So let's say we had our x and our y graph, or our x and our y axes, okay? And let's say it's 3 right here, positive 3. Make sure, yeah, I'm going to follow along in the book. What these graphs or what these functions typically have are asymptotes. And there's a vertical asymptote and a horizontal asymptote. Now, asymptotes are really just where our function can exist. Okay, it's like a fence in a way. And visually on a graph, it'll look like this. If I have a vertical asymptote, it will put a dashed line. And if you've got your book open, you can see what I'm talking about on page 406. I'm in your homework, actually. On page 406, there's 2 graphs there of these rational functions, and they have these vertical lines on them. Those vertical lines are called vertical asymptotes. vertical asymptotes. Now we're going to go into the algebraic process of finding a vertical asymptote next, okay? But for now, I just wanted to show you what these look like on a graph. A horizontal asymptote, let's put a horizontal asymptote right here at -1. Actually, let's do -2. -2 here. Put a dashed horizontal asymptote. So here we've got a horizontal asymptote. Okay, a horizontal asymptote. So we've got a vertical here, we've got a horizontal here. And what happens, I'm just gonna make up this graph. This is me just making it up, okay? I'm gonna make up a graph, but we'll notice that the line, as it gets closer and closer to the vertical asymptote, it's gonna either go really high north or really far south, okay? Really high north or really far south. Now the horizontal asymptote though is more about the end behavior. As the line goes further west, it's going to get closer and closer to a horizontal asymptote. And the further it goes east, it's going to get closer and closer to our horizontal asymptote. So if we looked at one, let's say we just started here for whatever reason, it's going to do this. As we get closer to the vertical asymptote, we're going to go, let's go north on this one. And as we go west here, it's going to get closer and closer, but it's never going to cross this at the end points, okay? All the way. Now, it might cross the horizontal. It'll never cross the vertical asymptote because really these verticals are coming from our restrictions, okay? We'll see that in a minute. We'll tie these together in a minute. And so then let's say on the other side of the vertical, it does this. So something like that. Okay, it does something like this. So that blue line there, I'm not sure if you can tell that this is blue, but the blue line is our actual graph. And as we get closer and closer to x equals 3 here, 1, 2, 3, our line goes really high north, okay, really high in the sky. But on the other side, it goes the other way. As we get closer and closer to 3 on this side, it goes further south, right? Further south for the sound effects, right? You're not even paying for that. That's extra for free. And then the further we go to the right, we're just going to get closer and closer to the horizontal asymptote, and then further to the left, closer and closer to the horizontal asymptote. So I'm going to introduce some math notation now. And I need you to follow along. And if you're watching this video later, it makes complete sense to pause it and watch it again. This is it's like learning a new language, right? Math, algebra is a language in itself. And sometimes it takes seeing it 2 or 3 times. And I understand that. So Jeanette, if you need me to stop, just ask a question. You get to represent all the students right now. So if you have a question, please stop and ask me. Because I'm about to ask you to really pull information from this graph. And we haven't done this yet. You might not have ever done this before, okay? And it's in the homework, it's on 9 through 19. This is how the homework looks. So let's look. We're going to focus just on this graph. Now look, this has nothing to do with that previous example, okay? Just on this graph. And I'm going to say, I'm going to write it as the book does. As x approaches, we're going to go to 3 here. Look, 1, 2, 3, 4, 3. As x approaches 3, now that little arrow means approaches, okay? So in math terms, this means approaches. So as x approaches 3, now look, you can approach 3 from 2 different sides, right? You can approach it from the left, or you can approach it from the right. And the way you deviate between the two is using a negative or a plus in the exponent. So if we want to come from the left, we're going to use a minus sign. We're going to use a little minus sign there. And if you look in your book, like number 9, if you've got your book out, they do the same thing. Now they approach -3, but they're approaching it from the left. From the left. From the left. So what this means, this is that math language stuff. As x approaches 3 from the left, we want to know what y is doing, okay? So we put a comma here and we go, well, what is our y doing? Remember, f of x is just a fancy way to say y. We want to know what the heck is y doing. And then we've got to go back to this blue graph. Because look, we're going to follow this blue graph now. And as we get closer on the x-axis to 3 from the left, so where my finger is at, right? I'm getting closer to 3 from the left. Notice that the y values, look, my y value here is 1. My y value here is about 3. My y value up here is going to be like 9. And then it goes forever up, okay? Forever up. So what that means is as x is approaching 3 from the left on our blue line, right? I mean, look at the x values here. -1, 0, 1, 2. Well, the y values are going to positive infinity because it's going up, okay? The y values are going to positive infinity because that blue line is going up. Because the blue line's going up. So let's flip this. Let's say as x is approaching 3 from the other side. So now we're going to use a plus sign. A plus sign here. And this means from the right. Say from right. I don't know how well you can see that on your screen. It's kind of hard to write. So, but that's a plus sign now. So now we're going to be approaching 3 from the plus sign, from all the positive values, right? From this side. And we're going to get closer and closer to 3. And we want to see what's our y value doing now. Okay? What is our y value doing now? And notice, if we're approaching it from the right, our y value is going now down. So it's going to negative infinity. I mean, think about this. If we chose coordinates along the way, like this coordinate would be like 5, right? And it's at like -4. This coordinate's 4. So we're getting closer to 3, right? 5, 4. This is 4, and the x value is 4. The y coordinate's like -6, 5. And then as we keep getting closer, though, from 4 to 3, that little gap, it just goes down forever, okay? It goes to negative infinity. That's what happens with a vertical asymptote. With a vertical asymptote, as you go from both sides of an x value, so for us it's 3, your f of x, your y value is either going to go to positive infinity, negative infinity, or it might do 2 separate ones, but it's not going to run into each other, okay? It's not going to run into each other. A vertical asymptote causes this diversion, okay? It causes a diversion. And for this one, from the left, it went to infinity, and from the right, it went to negative infinity. So now let's talk about end behavior. We've already talked about end behavior, right? End behavior is what happens at the end of the graph. And with polynomials, end behavior just went up or down, right? On both sides. On the right, it went up or down, and on the left, it went up or down. Well, when you have a horizontal asymptote, that's not going to happen. So with horizontal asymptotes, now the way you would notate end behavior is as x approaches either one of the infinities. So let's do positive infinity. What happens when x approaches infinity, right? When x gets bigger and bigger and bigger. Now let's look at this. As x is getting bigger, like 4, 5, 6, notice the y values here are getting closer and closer and closer. And it would just keep going like this. Closer and closer. It's a leveling out. It's not going up. It's leveling out. It's getting closer and closer to our horizontal asymptote of -2. So f of x is actually headed towards, sorry if I'm covering that up, f of x is actually headed towards -2, okay? That's a negative there, -2, because that's where our horizontal asymptote is. It's at -2 here, -1, -2, -3, okay? This would be true on both sides. Look, what about when our x heads to negative infinity? What happens on the left side? Is it rising? Is it decreasing? Or is it leveling out? Well, it's leveling out. And where is it leveling out? It's always going to level out at its horizontal asymptote at -2. Holy cow, it is humid as heck in this room. I'm going to be sweating at the end of this lecture. Okay, Jeanette, you're getting a private lecture right now. Do you have any questions before I go on? You can give me a thumbs up on there if you're just not wanting to. Thumbs up means no questions. I'll take that as me just ready to rock and roll. To the next part. Okay. All right. And I'll tell you, this is one of, look, there was no math involved. I'm not telling Jeanette this, I'm telling all of you this. There's no math involved here. There was no algebra involved. But this is easily the #1 missed question on the test, hands down. Okay. This is the #1 missed question on this test. I'm going to give you a graph and I'm going to ask you things about the graph. This might be A, B, C, D, or I might just choose 1 or 2 of these. Okay. And it will be the #1 missed question. And there's no algebra involved. You don't have to plug things in. Maybe that makes it a little harder. There's no solving, right? It's really interpreting from a graph what's going on and knowing the language. So just be careful. It's on the test and it's a very common missed question because it's a very visual question, okay? So that leads us actually into the algebraic aspect of these rational functions. So let's look at a basic example first. Let's say I've got f of x equals, let's say, it doesn't really matter what's on top. Let's say 3 over x minus 2, okay? F of x equals 3 over x minus 2. Now we have a polynomial on top and bottom. The numerator polynomial is 3. The denominator polynomial is x minus 2. And I'll tell you, the first question in any of these, when you deal with the rational function, is the domain question that we've already gone over. So the very first thing I'm going to ask you is, well, what's the domain? And you're going to go, oh, yay, I know how to do this. I just set the denominator equal to 0, really not equal to 0, right? And I solve it out, add the 2. And I find out that x cannot be 2, right? Now, to make Mr. Shirley in the book happy, I'm going to write it like this because that's how my domain's supposed to be written. But then hopefully the idea pops into your head, well, what is happening at 2? Why can we not be 2? Well, we can't be 2 because if we plug 2 in, now this is just extra work here, but if I tried to plug 2 in, I'd get 2 minus 2, I would get 3 over 0. And remember, this was one of those glitches in algebra, right? We don't know what happens at 0 at all. We don't know because we just haven't figured it out yet. If you want to figure it out, you can get your name on something and people will be talking about you in algebra books for a long time. But for now, this was just called undefined, right? We just called it undefined. Well, then mathematicians thought, okay, I don't know what happens at x equals 2, but I want to know, right? Dang it, I want to know. It's a mystery. I want to know what's actually happening at 2. Now, I'm going to do a goofy analogy here about how to figure out what's going on at 2. And it's one of my favorite goofy analogies I get to do every semester. And it says, well, okay, let's say which I don't know if people go on blind dates anymore, but let's say you were set up on a blind date, okay? And you're set up on a blind date with the number 2. And you wanted to figure out everything about this number 2, okay? Now, the one thing you can't do is call number 2 and ask them what's going on, right? Or tell me about yourself. You'll get to do that at the blind date, but you can't do it now. So if I wanted to know about this number 2, I would do probably what most people do now. And I would start social media stalking them, right? I would get on their social media, see if I can find them online. That would tell me a lot about who they are, right? And I might even ask people that are around number 2, right? Maybe kind of like casual acquaintances of number 2. What do you think of number 2? Are they a positive person or a negative person? Pun intended for positive and negative numbers, right? Or what do you know about them? So if I wanted to know about the number 2, I could really start asking or figuring out the people around number 2, and the people that are the closest to number 2 will tell me the most about number 2, right? And that's exactly what we do. That's exactly what we do, which is kind of crazy. We start figuring out what what happens with the numbers, the x values, right? Because it is an x value. What happens to the x values around number 2? Now, this is called, I don't know exactly what it's called, but it's approaching 2. We're going to approach 2 in an algebraic way. So as x approaches 2, we talked about this earlier, we're going to go from the left first, and we're going to do this in an algebraic manner, not in a visual manner. I'm not giving you the graph and then doing it. We're going to do an algebraic manner. And so what I'm going to do is I'm going to make a table. Okay, I'm going to make a table, and I'm going to get closer and closer to 2 before I get an idea of what's going on there. Okay, so let's start with a number that's kind of close to 2 on the left. So I'm going to start with like -1. Why not? I'm going to do -1, and then I'm going to do 0, 1, right? See how these are approaching 2? And then I can't do 2, right? So, but I've got to do numbers to the left of 2. So maybe I'll do 1.5. And then I'll do 1.9, right? And then 1.99. I bet, look, these are acquaintances. These are close relatives, right? 1.99 is very close to 2. By the time I get there, I'll get an idea of what's going on here from the left, okay? I'll get an idea of what's going on here from the left. Now, I'm going to bust out my calculator, and I'm going to just start plugging these in. And so I'll do this to make sure we get the same thing. So if you want to take your calculator out, all we're going to do is plug this value into here. Now, I'm going to show you an easy way to do this with these calculators. And I'll do the thing where I put the calculator in front of the screen. So the first thing you need to do actually is click on, let me move this around a little bit. Hopefully this helped last time. No one told me if it did or not. That y equals button, click that, and we're going to make that equation the y equals in here. So to do that, you need to put parentheses around the top. And I know some of you are going, no, you don't have to. Well, it's a really good habit to. Notice I put parentheses 3 and then divide, and then I'm going to put my denominator. Now remember, to get the x in here, I've got to press the x comma t comma theta button. So I opened up a set of parentheses. I did x. I'm going to do the minus key, which is down here somewhere. Minus, was it 2? And then I'm going to close this set of parentheses. Boom. Okay. Now, what's neat is your book you can put numbers in and it'll give you back numbers. So if you hit, I think it's second calc. Nope, that's not right. I got to remember what button to put in. Hold on a second, guys. It's been a minute since I've done this. This is good. Oh, yeah, it is. Okay, so one easy way to do, once you have that equation in there, you can hit, where are you at? There you go. Notice above the trace button right here in blue, or it might be some other color, but it says calc. You can hit second and then calc to bring that up and hit the value button. Boop. And now if you put in an x value, it's going to give you back the y value. So our first x value is -1. I'm going to put in -1. And it's going to pop back. It's really small right there, but it looks like -1. Yep. So for x equals -1, we get back y equals -1. Now, if you're going, well, Mr. Shirley, it's just a lot easier to plug that in and get the 3 divided by -1 minus 2, that's -3. 3 divided by -3 is just -1. You're right. This is nicer whenever we start putting big and small numbers in. So let's put in 0. I'm going to do second calc value 0. And I get back -1.5. -1.5. Now I'm not going to do that. I'm going to just stand here and do this now, Cass. I'm going to put in second calc value, was it 1.5, right? Or no, just 1. 1, I get back -3. 1.5, let's do that one. I get back -6. 1.9. I get back -30. 1.99, I get back negative 300. Ooh, that was a jump. And I'm going to guess for 1.999, I'd get back negative 3,000. Okay. Well, let's talk about what this means algebraically now. So what this means is, look, as x is getting closer and closer to 2 from the left, right? We're coming from the left. Our y value is headed to negative infinity. Do you guys see that? We're not headed to a specific number. This goes off the deep end in the negative direction. So look, this is headed towards, it went negative 1, negative 1.5, negative 3, negative 6, negative 30, negative 300, negative 3,000. Look, this was a little bitty jump here. Negative or 1.99 to 1.999 is a 0.009 jump. And on the x-axis, but on the y-axis, it was a 2,700 unit jump in the negative direction. So kind of crazy there. And what this means is that as x is approaching 2 from the left, f of x, our f of x right here, is going to negative infinity, okay? Our f of x is going to negative infinity. So I could kind of sketch this a little bit. Draw what's going on. Actually, let's go from both sides first. Let's do the other side now. So now, let me kind of box this out so I can use it. What about as x is headed to 2 from the right? I wanted to know what's happening now. So I'm going to do the same thing on the other side. Now, I'm not going to use as many numbers just because we can see what's going on with less numbers now. But I'm going to say x, and I'm going to say f of x. But now I've got to come from the right. So I'm going to just start with like 4, 3. I can't put 2 in. 2 is going to give me undefined. Let's say 3.5, 3.1, 3.01. Maybe we'll see a nice pattern and we can just fill it in. Okay. Now look, 4 I could do in my head. 4 is 2, or 4 minus 2 is 2. So 3 divided by 2, that's 1/2, 1.5. 3 I can do in my head as well. 3 minus 2 is 1, right? So 3 divided by 1 is just 3. 3.5, if you can do that in your head, you're more than welcome to. I'm going to use the calc button again. So remember, second calc value, 3.5. We get, oh, I did something wrong. I did something wrong here. I got y equals 2. What did I do wrong? Oh, I know what I did wrong. This isn't getting me closer to 2. This is getting me closer to 3. I need to put 2's in here. It's 2.5, 2.1, and 2.01. That gets me closer to 2. Okay, so value 2.5, and I get 6. 2.1, I get 30. We got the same thing going on, but it's a little different. 2.01, I get back 300. So I'm going to assume 2.001, I get back 3,000. So we have the same sort of pattern. It's just not negative, right? It's just not negative. Now, as we're getting closer to 2, our y value is going to positive infinity. Our y value is going positive infinity. So let's graph what we've got going on here. Let's graph what we've got going on. So as x, well, we can't plug in 2. So actually, what we're going to do for this one, and because these go to infinity, that means we have a horizontal asymptote at x equals 2. So I'm going to graph that. I'm going to draw the little dashed line for the horizontal asymptote, okay? Because x goes to infinity for both of those, we know we have a horizontal asymptote. And then I'm going to kind of graph it. You can see the graph in your book. It looks like we have a horizontal asymptote as well. We're at 0, we're at 1. So it looks something like this. It's not perfect, but it looks something like that, right? And we can see from this, actually, we have a horizontal asymptote going on as well. Now, horizontal asymptote, if you're going to use the table method, you would start putting in huge numbers. And I'm going to do that. I'm just going to do it for the right. So as x goes to infinity, what's happening at f of x? Now it looks like it's headed towards 0. Let's see. So my x values, I'm going to put in big numbers now. And I remember the cell function. So I'm going to put in like 100. Actually, let's put in 10. Then 100. And then 1,000. And then 10,000. It might break your calculator. And I hope not. But let's see if it does. So if we put in 10 here, second calc, I'm doing the same thing, right? It's the same equation, just different tables. So if I put in 10, I get back 0.375. I get back a really small number. So what if I put in 100? Nope, I get an error number, and it's because it's really, really small. Let's actually do this one by hand. If I put 100 into this, it would be 3 divided by parentheses, 98, right? 0.0306122 . Well, let's put in 1,000. So I'm going to do 3 divided by 998, right? 1,000 minus 2 is just 998. Oh, we get 0.003006012 . Right? Well, this is this is a lot different than these two examples. This is not headed to an infinity, right? It's headed to a very specific number. Let's do 10,000. So that'd be 3 divided by 9998, right? 9,998. You get scientific form 3.0 times even. And what that means is we've got 4 decimal places to the left of 3. 0.612. Okay, look, we're going to talk about this for a minute. What's happening here algebraically, look, as x is getting larger, it's going to infinity. Our y value, it's not headed to an infinity, it's headed to 0. It's headed to 0. Look, this is getting closer and closer and closer to 0. Pretty cool. Okay, pretty neat. It's headed to 0. And that's actually what our graph is showing as well. Look, as x is getting bigger, the y value is headed to 0. Same thing's happening on the left-hand side as well. It's headed to 0 as well. Kind of cool. Okay, kind of cool. Okay, so for the last 30 minutes here, we're going to talk about how to do all of this algebraically. And you're going to go, why did you go through this? This is the hard way to do this. And you're right, it is the harder way to do it, but I have to show you the fundamentals, or the math gods, they'll come down and they'll strike me, and then I might get taken away. So let's now go over really kind of the shortcut to do this, okay? And because we've got to talk about one other thing that could happen. And so I am going to do one more long ways. Sorry, guys. So let's do one more, but I'm going to do this the long way, and then we'll get to the short way. What if we had, let's do x squared minus 4 over x plus 2. So a little different. So x squared minus 4 over x plus 2. And again, I'm going to ask you for the domain. So very similar to before, x plus 2 can't be 0. So x now can't be -2, right? X can't be -2, and you'll tell me it's -2 to or -infinity to -2 union -2 to infinity, right? But then we want to know what's happening at -2. So I'm going to do this just from one side, and we're going to see something interesting, okay? So we're going to go to -2 now. As x approaches -2. So let's do it from the left. So -3, -2.5, -2.1, and let's see what happens. Now, again, I'm going to go into my calculator, and I'm going to put the graph in here, go to y equals, clear this thing out, right? And then I'm going to say parentheses, x squared minus 4, close that set of parentheses. I hope you guys can see this. It's not really coming through well on my screen because of the glare. Divided by x plus 2, right? X plus 2, okay? Real technologically savvy. So when I do this now, I'm going to do that second calc again, and and I'm going to do the value. So I'm going to put in -3 here. Oh, it's graphing it. Oh, and you can tell on the graph there's no asymptote. If you look at that graph, there's no asymptote. If I put in -3, I get -5. If I put in second calc -2.5, oh crap, I hit the wrong button. Value -2.5, I get -4.5. I get 2.1, so second calc -2.1. I get back -4.1. You know, this is totally different than the last example. This is actually headed not to infinity. It's actually headed to a number. Let's get a little closer, -2.01. We get -4.01. Okay. This is headed to a number. This is headed to -4. So as x approaches -2, our function is actually headed to -4. Will it ever get there? No, it will not, because x will never get to -2. It's not in its domain, okay? So quickly, I'm going to do the same thing on the other side. As x goes to -2 from the right. So if it goes to -2 from the right, it would be like -1, from the right would be -1, -1.5, -1.9, -1.99, right? This will get us closer and closer to -2. Now I'm going to do the same thing, just second calc value, -1, I get -3. Second calc value, -1.5, I get -3.5. Oh, we're getting the same kind of thing. Second calc value, so am I. -1.9, I get -3.9. Oh yeah. Oh shoot. Second calc value, -1.99. I get back -3.99. Same exact thing, right? Look, as x is headed to -2, from the right-hand side, I'm also getting closer and closer to -4. It's not going to an infinity. It's going to a very specific number, -4. Now, if this happens, it means instead of a vertical asymptote at our restriction, we have a hole, okay? And if we wanted to graph this, you can see on your graph, it's just a straight line, but it doesn't show you the hole. The hole is going to be at -2 and -4. -2, -4. There's a hole there. We can't be -2, right? We can't be -2. Our domain says that. And if we can't be a certain value because of a denominator restriction, it's either going to be a vertical asymptote or it's going to be a hole. Those are the only two things that can happen. So if we have a distinct restriction, a distinct number that's a restriction from our denominator, it's either going to be a hole or a vertical asymptote, okay? And with rational functions, I should put it like that, with rational functions with this section. Now, for this instance, it turned out to be a hole. And so we wind up with something that looks like this. This is actually what the graph should look like, but you just can't see it in your calculator. If you're looking at your calculator now going, but there's no hole there. Yeah, it's because it doesn't show that. If you try to put -2 into the calculator, you'll get an undefined because it can't give us back the value for -2. Okay, so now I know I kind of sped through that, but let me show you algebraically why this happens. Okay, let me show you algebraically why this happens. I'm going to use this example. So I'm going to say A, domain, question mark, B. Okay, with that restriction, is it a vertical asymptote? Or, we'll just say C, is it a hole? Now we know it's a hole, we already did this. But I'm going to do this algebraically to show you don't have to go through that whole table process. The way you find this, if it's a vertical asymptote or a hole, you need to go back to the original function and factor completely. Remember at the very beginning of this chapter, I said you have to know how to factor completely. Well, this is one of the reasons. We have to factor the numerator and denominator completely. So if we look at this numerator, x squared minus 4, it factors. X minus 2, x plus 2. It's a difference of squares. The denominator, x plus 2, right? Okay. If your restriction cancels, it's going to be a whole, okay? If your restriction in the denominator cancels with a factor in the numerator, it's going to be a whole. So if we look at this x plus 2 and x plus 2, boom, it cancels. It leaves us with x minus 2, which looks like it doesn't have a restriction. Now it does because of the original function. And notice where our restriction occurred. So we don't have a vertical asymptote. I'm going to put a big circle with a line through it because that means there's no vertical asymptotes, no solution for vertical asymptotes. But we do have a hole. And holes are coordinates. So look, we've got a hole at x equals -2. And what you do is you plug that into the simplified function. So if you plug -2 into the simplified function, you get -2 minus 2, you get -4. That's that y value. Now remember, if you go back, that's where we drew our hole. So that's how you get this algebraically. If you did not want to use a table every time, this is how you would get it algebraically. Now, if it doesn't cancel, it's a vertical asymptote. I'll do one of those next, okay? Actually, if you go back to the example before, which looked like this, 3 over x minus 2, right? 3.
If you have two negatives, how can it be negative?
Well, -2 minus 2 is -4. You're thinking of multiplying, Jeanette. Remember, if it's minus 2 minus 2, it's -4. Good question. So let's go back to that previous example, and I'm going to work this one algebraically instead of having to do all the tables. So the function looked like this. F of x equals 3 over x minus 2. Now, we found the domain. I'm going to scoot along here. We found the domain already. It turned out that x can't be 2, right? X couldn't be 2. Now, look at this, though. The difference in this one is that the numerator and denominator, neither one of those factor. So nothing cancels out. If nothing cancels, we do not have a hole, okay? And what we're left with are vertical asymptotes. So remember, this restriction is either going to be a vertical asymptote or a hole. If we go up here, it doesn't cancel. So therefore, we've got a vertical asymptote. Now, it's a vertical line, so it's x equals a number. It's x equals 2. Okay, it's x equals 2. Okay. So let's do one more of these before we start talking about the horizontal asymptote. So I'm going to steal one from the book here. Ooh, man, my back hurts. Yeah, this is g of x equals. Now I'm going to write it a little different than the book, but let's say it's x over 3, x squared minus 3x, okay? X over x squared minus 3x. This is just an example. It's not really in the book. I'm just kind of making it up, though, but it would fit in the book. So remember, the first question on these rationals is going to be, what's the domain? What's the domain? Well, we set that denominator not equal to 0, and we solve it. Now, what's nice is if the denominator factors, we're going to do it now, okay? So you'll see what the denominator factor will be right after this first step. So if I look at x squared minus 3x, I can factor an x out. And I'm left with x minus 3. So that's my factor version. That'll help us out up there. We've got x can't be 0, right? We have to set each one of these equal to 0. And x minus 3 can't be 0, so x cannot be 3. Those are our two domain restrictions. I'm not going to write it out. Don't tell anybody. I'm not going to write it out in the interval form. But now we have two restrictions in our denominator. So what this means is that x equals 0 could be a vertical asymptote, or it could be a hole. Same thing with 3. 3 could be a vertical asymptote. 3 could be a hole. So I'm going to put B, vertical asymptotes or holes. Okay. And remember, the way to figure out if it's a vertical asymptote or a hole is to go back to the original function and factor it completely. So if we look at this, on top we've got the x. On the bottom, the x factored out. We did this already right here, right? And we're left with x minus 3. And that x value cancels. It's a factor in the numerator and denominator. So this x value cancels in both spots. So what that means, actually, let's simplify this down. So this would be 1 over x minus 3. But what that means is that x equals 0, that's where that factor came from, right? That's where that solution came from. X equals 0 is going to be a whole. We've got to find the y value. We'll do that in a minute. But that x equals 3, that didn't simplify out. So that's a vertical asymptote. So x equals 3 is a vertical asymptote. Now, to find the y value, remember the y value of the whole, I should say. To find the y value of the whole, we go to this simplified version and we plug in the x value. So I'm going to plug in 0 into the simplified function, and I would get 1 over 0 minus 3. I get negative 1/3. So I wind up with 0, negative 1/3. That's my whole. Okay. And if I wanted to do a quick sketch of this, let's see what we have going on here. We've got 3, x equals 3 is a vertical asymptote. 0, negative 1/3 is, so about right there, is a whole. Now we need to find the horizontal asymptotes, okay? And I'm going to find my first horizontal asymptote, my first example with this example, I should say. So A, B, C, D. Let's now find horizontal asymptote. Now I'm going to go over it with the example here. Now this is going to feel like it's really out of left field, but horizontal asymptotes have to do with degrees of your numerator function and your denominator function, okay? So let's go back to this original function here. The degree of the numerator. I'm only going to write this out long ways once. If I look at the degree of this numerator, it's 1. Remember, it's just the highest degree variable, 1. The degree of the denominator. The degree of the denominator here is 2, right? We got x squared minus 3x. The highest degree term is 2. Okay, the degree of the numerator is 1 and the denominator is 2. It turns out if the degree in the numerator is greater than the degree in the denominator, there's automatically a horizontal asymptote at y equals 0. So we didn't have to do any math there. There's a horizontal asymptote at y equals 0. I'll give you the other two things that can happen in a minute. But for this one, if the degree is no, not just for this one, but for all of them. If the degree is larger in the denominator, we have a horizontal asymptote always at 0. So if we go back to our graph here, what this means, y equals 0 is right here. We've got a horizontal asymptote right there. So our graph looks something like this. Now it's got to go through the hole, but you kind of jump over. And on the other side, something like that, okay? Looks something like that. So if I started there, I could ask you, well, as x approaches 3 from the right, oh, it goes to infinity. 3 from the left, negative infinity. Oh, the end behavior, oh, it's 0. As x goes to infinity, we get closer and closer to 0, okay? It all kind of comes together here at the end with this stuff, okay? So let me keep going. I don't have much time, and I want to cover the other things that can happen with this horizontal asymptote. So I'm gonna think up another example here. Falling apart. Let's say we'll do one that's a little different. Let's say f of x equals, let's say x squared plus 2x over x plus 2. Okay, x squared plus 2x over x squared plus 2. Always starts in the same spot, okay? A what's the domain here? You're saying, oh, well, x plus 2 can't be 0. It's just x can't be negative 2. Okay, not a big deal. And I want to know, is that going to be a vertical asymptote? Or is it going to be a hole? Okay, is this going to be a vertical asymptote? Or is this going to be a hole? So to do that, remember, we've got to factor the numerator and denominator completely. So I'm going to factor the numerator. I can factor an x out. I'm left with x plus 2. And I factor an x plus, oh, well, x plus 2 is already down there. And look, this cancels on top and bottom. Boom. That x plus 2 cancel, or x equals negative 2, right? Cancel. And because of that, that means there's a hole. There's no vertical asymptote here because the denominator canceled completely. And it leaves us with our hole at x equals negative 2, right? It leaves us with our hole at x equals negative 2. And if you take negative 2 and plug it in now, you're going to get y equals negative 2. So our hole is at negative 2, negative 2, okay? Our hole's at negative 2, negative 2. We've already done an example like that, but that's remember where the denominator cancels completely. So now what about horizontal asymptote? Actually, let's just call it HA so I don't have to write it all out. Well, we're going to look at the degrees of the numerator and denominator again, and notice these are different. The numerator degree is larger. So the degree of the numerator is 2, and the degree of the denominator is 1. So we flipped it. The degree of the numerator is 2, and the degree of the denominator is 1. Well, if this happens, we actually have no horizontal asymptote. And you can do a circle with a line there if you want. But if the degree is larger on top, there's no horizontal asymptote. If you wanted to graph this, and you can pop in your calculator to see, it turns out to be the graph of y equals x, except negative 2 has a hole. Like that. Okay, it looks something like that. Okay, something like that. But if the degree is larger on top and the degree on the bottom is smaller, right? 2, 1, then it turns out we just don't have a horizontal asymptote. Notice this doesn't go down, right? There's no, and this one didn't have a vertical asymptote either, which is kind of neat. Okay. Okay, the last type of example is what if the degrees are the same, right? What if the degrees are the same? So let's go back to this f of x. We'll say it's, let's say 2x plus 1 over 3x minus 4. I think this might have been the example we started with at the very beginning. If not, it's pretty similar. 2x plus 1 over 3x minus 4. And I'm going to do the same exact thing. I'm going to find the domain first. 3x minus 4 can't be equal to 0. So x can be add the 4, divide the 3. We wind up finding out that x cannot be 4/3. Okay, negative, positive 4/3, yeah. X cannot be 4/3, but we need to know, is that a vertical asymptote or is it a hole? Well, if we go up here, look, check this out, guys. This does not cancel. This doesn't cancel. The denominator and numerator do not cancel. Nothing factors, which is kind of nice. You didn't have to remember how to factor anything. So therefore, it's not a hole because nothing cancels. And it turns out that this is just a vertical asymptote. Oh, not B, but x equals 4/3. Okay. But the main difference is that these degrees are equal. Okay. If degrees are equal, this one's a little weird. If the degrees are equal, you've got a horizontal asymptote at the ratio of the leading coefficients. the ratio of the leading coefficients. So what does that mean? Well, let's go back to our equation. The leading coefficients of the numerator, the leading coefficient of the numerator is 2, and the leading coefficient of the denominator is 3. So we have, since the degrees are equal, it's 1 on top and bottom, we have a horizontal asymptote at y equals 2/3. Kind of cool. Okay? So if we were going to graph this, zoom in here. 2, 1, 2, 2. We've got a vertical asymptote at 4/3. Well, that's like 1 1/3. It's about right here. We've got a horizontal asymptote at 2/3. That's about right there. And if you wanted to graph this, you can. It looks something like, hold on. Oh, let's see. So it looks something like this. You can pop that in your calculator and see it. I'm not too worried about it. But we found the vertical asymptote and the horizontal asymptote. Pretty neat. I know. You don't have to tell me. I know these things are cool. Okay. I want you to do 1 through 43. This is on page 406, so section 3.5, page 406, 1 through 43. And then, okay, from 57 to, let's do 57 to 73. Yeah. Yeah, 57, actually 57 to 69. I want you to do all odd. Now on this one, on 57 through 69, it asks about, the book goes over like a 6-step process to graphing. Don't worry about that. I want you to focus on this A through E here. Your book also goes over slant asymptotes. Don't worry about slant asymptotes, okay? I want you to focus on what we did here for numbers 57 through 69. Do not worry about the 6-step approach to graphing rational functions. I want you to be able to find the domain, if vertical asymptote in the whole, and the horizontal asymptote. Okay, and then the stuff at the very beginning, 1 through 7, or actually 9 through 19, I need you to be able to interpret from a graph. Okay, great. Jeanette, do you have any questions? Comments or concerns?
No, I'm good.
Okay, great. I will see you and the rest of the group on Tuesday. We'll go over the next section on Tuesday. I'm going to end the meeting. I'll see you.